Welcome to qnawire.
In this problem, we have a tank, and it has a piston in the middle of it. And the piston can slide. Well, in one case, it can slide, and in the other case, it can't. It's fixed. But we also have heat transfer across there. So in this side, we have nitrogen, and this side, we have helium. Initially, they're both at 100 kilopascals. And initially, the volume of both I guess I should put a 1 here. The volume of both of them is 1 cubic meter. Okay. Let's see here. Not allow you. Okay. So this is, again, this moves but doesn't allow any leakage of gas. So you have everything over here stays over here and everything over here stays over here. Now we can get the ideal gas constants for the nitrogen and for the helium, the heat capacities for each of the gases, and we're also going to wind up using the universal ideal gas constant. Now, we can figure out the mass of the nitrogen because we know the pressure, the volume, and the temperature, and the ideal gas constant for the nitrogen in the first state. So that winds up being 4.772 kilograms. We can also figure out the mass of the helium over here, and that turns out to be 0.8079 kilograms. So a lot less helium over here, although we have the same volume. Again, helium is a kind of a very, very low density. So then we can say, okay, now if we take a control volume of the whole tank here, we know there's no work going in, it's rigid. There's no heat transfer coming in or out. So we know the change in internal energy has to be 0. And that change in internal energy is the change in internal energy in the nitrogen side plus the change in internal energy in the helium side. Now, we know then that when this whole thing comes into equilibrium, the temperatures on both sides are the same. So TB2 and TA2 are the same, and I'll call that T2. And this gives us an equation for T2 then. And solving, we get that is 57.2 degrees Celsius. I don't know if I actually mentioned that we had the temperatures in these sides is 80 degrees Celsius in the nitrogen, 25 in the helium. So we're, in somewhere pretty close to being in the middle. So what is 105? 105 over 2 is, 52.5. So a little bit over halfway here. So it's kind of surprising with the heat capacities this way, but the fact is that we have a lot less mass of helium. Now, we want the entropy generated. So the entropy generated is just the change in entropy in each of the gases, all right? And so to get that, we need to, we know we have the total volume here, right? We don't know that after this whole process takes place, we don't know where this piston is, right? So we don't know the specifics of the volume of each side. I think we could find that, but the easiest way to do this is to just say we know the total volume. The total volume doesn't change, and the total volume is 2 cubic meters. And we also know that this whole thing is at the same temperature. And so if we know the number of moles of gas in here, it doesn't matter what type of gas it is. If we know the number of moles, then we can use the ideal gas law to find the pressure in here. And that's because, again, we're assuming that this thing has equilibrated. This thing is maintaining a constant pressure here. I mean, there's no net pressure pushing this either way. So the pressure on either side is the same afterwards. Now, to get that pressure, we need to, we use the ideal gas law, but we need first the number of moles of gas we have in here total. So the number of moles of gas we have in there is the number of moles of helium, or in the helium, and the number of moles of nitrogen. And again, we know the masses of each of these things, and we know the molar mass of each of them. So for nitrogen, it is what 20? Let me 28. Yeah, 28. And for helium, it is 4. So that gives us a total number of moles of gas in this tank of 0.3724 kilomoles. That we know that now, put that into here. We know the universal ideal gas constant, we know the temperature, we know the volume total of the tank. And that will give us the pressure in the tank as 511.1 kilopascal. So the pressure went up a little bit after this process finished. So again, we created a little pressure in this tank. Now, for the exergy destroyed, we need the entropy generated. And we needed the pressure because we needed to figure out what the entropy was, because that we need the pressure in there. So the entropy generated, again, is just the entropy generated in the nitrogen plus the entropy generated in the helium. But for both cases, the same formula applies, so just for ideal gas case. We know T2 is the same, P2 is the same for both. We have a difference in P1 and P1 for the two gases, and obviously these factors here differ, and the amount of mass. So we can calculate delta SA and delta SB, basically both from this formula. Doing that, we wind up with 0.0303 kilojoules per kilogram Kelvin of entropy generated. Multiplying that by the surrounding temperature, which again, I always forget to write that in here. The surrounding temperature was told to be 25 degrees C. So multiplying that by 298 Kelvin, we wind up with an exergy destroyed of 9.3 kilojoules. Now, the second part of this problem, which makes this problem extremely long, this is also the wasted work potential. Obviously, this is the wasted work potential that we didn't get out of here as this process ran. Now, we also said what would happen to the answer if the piston were not free to move. Okay, so now let's say we put a pin in here, right, and we hold this piston fixed. Well, we can see that one thing that we should notice is even if the piston was fixed, this temperature isn't going to change. And that's because it's only affecting the pressure. It doesn't affect the specific heat. And so if we look at how we got this temperature, we can see that the volume of whatever was in here didn't come into play here, and neither did the pressure. So if we went back and changed things, we would see that we'd get the same formula for the temperature in the final state. So in fact, that is then the same if we were to hold this piston fixed. Now the exergy changes, and it changes, and that we need to calculate that. So we go over here and we do that. So if a fixed piston, we have this again. Now, if the fixed piston, we have the volume in each side doesn't change, right? So that means that the change in entropy that we calculated over here from this equation for both sides, now because the volume doesn't change. Oh, what? Yeah, I guess we can write this as did I write that wrong? Well, yeah, I guess I should leave it as that in that form for that part of the problem. But let's see here. Leave it there, and I'll just write it again because we can also write that the entropy in this form, CV ln T2 over T1 minus R times the natural log of V2 over V1. All right. So yeah, because the volume doesn't change. So because the volume doesn't change, this term goes away, right? So we can cross that one out. So that's just another way of writing it, right? Because of using the ideal gas law, and knowing that the using the ideal gas law again. So in this case, we just have this term in the entropy, the change in entropy. So the change in entropy now winds up being this, or the sum of these two things. And then multiplying that by 298 Kelvin, we get now the exergy destroyed in this case is 6.23 kilojoules. So we destroyed less exergy by letting the piston, by holding the piston fixed, which is kind of an interesting observation to make. I guess basically we destroyed some by letting it equilibrate itself. Obviously, the pressure on both sides is not going to be the same in this case because the volume is the same. We could figure out what the pressure is in each side, but they didn't ask us to do that. So anyway, let's see here. I think that's all there is to say about that. So long problem, but we got it all figured out. They figured out the exergy destroyed. Temperature is the same, but exergy destroyed was less if we held the piston fixed.